Okay, here in the next one, we're going to take a look at one of our continuity problems. Basically, flow rates. What we're going to do is we're going to look at a garden hose, and I'm holding it with my hand. That is supposed to be a hand, not a very frightening looking spider. It's also disembodied. Use your imagination, assuming television hasn't killed it entirely. And it's got water coming out of it, because it's a garden hose, and that is what they do. Now the hose, when I'm initially holding it, I estimate that the hose has a diameter of about 2.5 centimeters, and that the velocity of the water coming out is about 1.5 meters per second. Now what I'm going to do is I'm going to put my thumb in front of it, These are really the worst hands I've ever drawn. And it's going to increase the velocity. And I want to find out how fast it's going. So, I'm pretty certain that roughly after I block some of it with my thumb, the diameter gets cut down to about 1.5 centimeters. Now I want to know what my velocity here is. Okay, well, from what we saw before, we know that our flow rate, Q, has to be the same, and we know that that is nothing more than our area times our velocity. And so if I apply this, I can take area 1 times velocity 1 equals area 2 times velocity 2. My flow rate always has to be the same because I can't very well destroy water, right? Putting my thumb in front of it doesn't make any of the water just magically disappear. It just changes the open space that it has, so now it gets pushed through much faster. So, this is a diameter, so be careful. We're going to assume that it's circular. And so our area is going to be pi r squared, which is our diameter divided by 2. If I've done the numbers correctly, the area here should come up to about 0.00196 square meters. Okay? And we know that our velocity is 1.5 meters per second. So that means our flow rate, area times velocity, is going to come up to 0.00295 cubic meters per second. Meter squared times meter per second gives me cubic meters per second. And we know that by continuity, the flow rate that we have here, the same amount of water is still coming out over here. It's just coming out faster because I've reduced the area. We know that this is then got to be equal to whatever's going on up here. So we need area 2 and velocity 2. And what we want is velocity 2. So area 2, when I go in and I use this diameter, I need to divide that by 2 to get my radius and convert that over into meters. Then I'll use it in pi r squared for area of a circle. Even though my thumb's blocking it, we're going to give it an effective area, so we're going to get something pretty close to what the opening is. And we're just going to estimate it, describing it as a circle. Okay? So A2, area 2, when I solve for that, comes up to 7.07 times 10 to the negative 4th meters squared. So a very small area, which makes sense. It's smaller than the area we had over here because I blocked off a significant portion of it with my thumb. Went down from 2.5 centimeters down to only 1.5 centimeters. And so we could see that it went from 1, 2, 3, about 2 times 10 to the negative 3. Well, it got cut down by probably a factor of 3 or so, which is noticeable. Okay, and so I know that my flow rate here, which is area 1 times velocity 1, that's 0.00295 cubic meters per second, equals 7.07 times 10 to the negative fourth square meters times velocity 2. I'm going to divide both sides by 7.07 e negative 4 square meters. Those cancel out. And then I evaluate this. I find that velocity 2 comes up to, if I've done this correctly, 4.17 meters per second. And this is an example of applying continuity. Now the same thing happens when you look at pipes and you have one pipe go from a large diameter down to a smaller diameter. You can do the same thing. Keep track of your diameters. You know that whatever water is coming through has to be the same. We're not creating or destroying water. And so you find your flow rates. Often you don't even need to find the flow rates at all. We could take area 1 times velocity 1 and just have the numbers and set them equal and get things to cancel out. But in this case, for thoroughness, I have shown the flow rate because sometimes we ask for the flow rate, the volume per unit time.